travel for millions or billions of years before it can be seen on Earth. By the time its light gets here, the star will be long gone, and it's too far away to gauge its speed or distance traveled with any certainty. The universe is expanding, only scientists cannot give precise answers about how fast. The mystery moves closer to being solved by imaging the cosmos with greater precision. Clearer images from space make it easier to estimate the rate of expansion.
If the universe continues to expand with time, then ultimately all of the energy sources, the nuclear furnaces in stars, would run out and die, and the universe would actually get very cold, and there'd be something called a big chill.
In the big chill scenario, Earth could become a lonely, cold planet as the universe expands. Distances between stars grow so vast that they nearly disappear from view. Over time, they burn out, and eventually the entire universe ends in a frozen state. This sphere demonstrates the principles behind a big chill. The marbles coming out of the sphere are like stars that were formed following the Big Bang. Dark energy propels the stars outward. Dark matter slows them down. In a big chill, the expansion would continue, but the nuclear fuel that causes the stars to burn will eventually run out. From Earth's perspective, the first thing to go would be sunlight. The sun dims as it exhausts its last bits of nuclear fuel. Earth would freeze and become lifeless. And billions of years after humans are gone, the cosmos expands out of view. A few newer stars might remain, but most would have long moved away. The furnace powering the universe burns out. The darkened universe continues to expand, a frozen and lifeless remnant of its once vibrant existence.
Eventually, if this keeps going, if nothing changes in the composition of this energy density, the universe will continue to expand forever. It's going to get colder and colder, and eventually even our neighboring galaxies will be receding from us so fast that we won't be able to see them. So the universe is going to get cold and dark, and it will be a very lonely place.
Astronomers have much to learn about the influence of dark energy and dark matter, and much of the newest information is coming from this probe in deep space. It's sending back information that's helping scientists to interpret the history and the fate of the universe. The night sky, by all appearance, is a quiet and peaceful place, but in reality, there are forces that are driving it to an end. Big science moves astronomers closer to deciphering the universe's great mysteries, including its ultimate fate. The solution to the universe's riddle may well be hidden in this multicolored image. What's incredible is that it's a map of the early universe from the moment it was conceived. And even more fantastic, it reveals a great story that helps cosmologists predict how it will end. The machine that captured this is called WMAP, a NASA satellite that's working around the clock to chart the cosmos.
What we're looking at here is the edge of the visible universe. It's the light that WMAP measured, it's the remnant heat from the Big Bang, and this is literally the oldest light in the universe that we can see. This fossil relic from the early universe tells us a great deal about what the composition of matter was like, what the expansion rate was like, and really what the conditions were at the birth of our universe.
WMAP is one of the great astronomical breakthroughs of the 21st century. Nothing before could give us such a clear image of the energy left over from the Big Bang, energy that scientists call the cosmic microwave background. WMAP is measuring temperature differences in the cosmic microwave background, which may finally make it possible to predict which force will dominate the universe and how that force will bring the cosmos to its end.
The blue spots are regions in the microwave light that was produced by the Big Bang that are slightly colder than the average temperature, and the red spots are regions that are slightly hotter than the average.
Temperature differences revealed by WMAP tell scientists about the nature of the matter and energy that is contained within the universe. They're able to analyze the light patterns and find clues not only about the substance, but also the fate of the universe.
We only capture a tiny part of the electromagnetic spectrum with our eyes, and we have to go to much longer wavelengths. The same wavelengths that are used to heat water in a microwave oven are what we're measuring here with WMAP.
WMAP is so precise that it can detect differences in temperatures as small as 1/1000th of a degree. This sensitivity helps scientists to calculate the ratio of dark matter to dark energy, forces that will determine how the universe ends.
We assembled all those difference measurements and make a map of what the variations look like. And by turning up the contrast, we can basically subtract off this uniform glow from the Big Bang and look for variation.
It doesn't look like much until Gary Hinshaw adjusts the contrast. Then the WMAP image comes to life. Looking at WMAP imagery is in essence taking a journey back through space and time so that we might get some new ideas on the fate of the universe. Pulling away from the probe and following the path of the light it is collecting, we pass Mars, Jupiter, and Saturn, whose reflected light takes over an hour to reach Earth. Then, leaving the Milky Way, we pass Andromeda, the next nearest galaxy, whose light takes 2.3 million years to reach us, which means we have traveled 2.3 million years back in time. And finally, we arrive back 13 billion years ago, at the beginning of visible light. Before that, superheated hydrogen gas is everywhere. WMAP can see this far back in history. It's confirming important facts about the universe and what's driving it to its demise. The final act for the universe becomes more easily predicted thanks to WMAP. Its information, combined with the work of astronomers, has led to some astounding discoveries concerning a rapidly expanding universe. Rapid expansion supports the dark energy theory and the possibility of a big chill or big rip.
We now know from all the data we've had in the last 10 years that there's, by a factor of 2 to 1, more dark energy than dark matter. So dark energy is the dominant constituent of energy in the universe.
The evidence seems clear. Dark energy is taking over and is leading astronomers into new thoughts about the beginning and the end of the universe.
Before the discovery of dark energy, things were a lot simpler. If we could determine the amount of matter in the universe, then we could say something about its ultimate destiny.
Those simple days are gone, but the proof is adding up and supports the idea that the universe will continue to expand. But will it do so to oblivion?
We've made huge strides over the last century in learning something about the evolution of the universe and its expansion. But we've now raised more questions in some sense than we've been able to answer. And so I think the next decade is going to be even more exciting.
Astronomers have tons and tons of challenges that have been thrown our way by theorists, and we are rapidly trying to figure out how to answer all of these questions. And I think that's the exciting future, because if you can go out and really observe something, you're testing it. And that's what science is all about.
The battle between dark matter and dark energy is expected to go on for billions of years, and humans will be long gone from Earth when the final outcome occurs. But no pursuit has been more significant to science than understanding how the universe arrived, how it works, and how it will end.
It's a never-ending quest. It's driving astronomy. What are the answers to these profound questions? The constituents of the universe, the nature of dark matter, and perhaps the biggest mystery of all, what is the ultimate fate of the universe?